Hi, everybody. I am going to post this article in the reference section of modules in Canvas, but I am just going to go through it now, and discussion of it will partly determine what we do next, or not next, but what we cover in the course. And I am going to give you just the outline of this. There are proofs and other things. I'm not going to go through those at this time. The purpose, I'm going to skim through some of this and get to I want to get my highlighter here maybe so I can highlight. Yeah, so I'll be able to highlight some stuff as we go through. So, this is the important part. The Common Core includes a fundamental change in the geometry curriculum. And what the change is geometric transformations, not congruence and similarity postulates. The usual congruence and similarity postulates are side angle side, 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 etc., that sort of thing. But instead of having those as postulates, we can prove those with geometric transformation axioms or assumptions that are higher level, really, but very intuitive than Euclid's. And so that makes it better for a whole lot of reasons. First of all, as it says here, congruence postulates are rather self-evident. And we use words like move and stuff like that when we talk about congruence anyway in geometry. And the mathematical arguments for the change are a transformational approach offers deeper links between algebra and geometry. Certainly that's true, and we'll see that. And then the natural way transformations connect with complex numbers and matrices can really enhance the teaching of these topics. And I put a follow-up survey under quizzes in modules. And I want you to take that, and that will deal with this sort of stuff. So by Friday is best. Please try to take that survey by Friday. It's the second one under surveys in modules quizzes. All right. And transformational approach can give symmetry a greater role. And we already started talking about that. Okay. And finally, and very importantly, this approach makes it possible to discuss similarity of curves, which could not be done under the traditional definition. And in fact, we can do that. We can talk about similarity of circles and parabolas and things like that. Okay. So a consequence, of course, is the need for some clarity in how this new vision affects the logical structure. And this article is intended for an audience of math teachers, as it says. It's not written for students, but you are very good, bright students, and so we'll go through the structure. Okay, some definitions are unchanged, and we don't have to say those. On the other hand, some definitions are new, and we've talked about these. We've talked about the definition of a transformation. Remember, it's one-to-one, and domain and range are the entire plane. That's the definition. And we talked about an isometry being a transformation that preserves distance. We defined reflection as, we just did it. And we defined dilation, and those are in the definitions document that I put. And we also define congruence now as two figures are congruent if they can be, one can map to the other by a sequence of isometries, and they're similar if they can be mapped by a sequence of isometries and dilations. In fact, we probably only need one dilation, and we can probably have it at the beginning or at the end, or specify its position. But I haven't proved that, but that's probably true. All right. Assumptions. This is very important. What are the assumptions? These are our axioms. Um, we are going to assume the parallel postulate, of course. We need to, because if we didn't, we would have non-Euclidean geometries. There are consistent geometries in which the parallel postulate is not true. And we can study those. Actually, I did that last year. If that's another topic, if you are interested in it. At least a special case is spherical geometry, geometry on the surface of a sphere, for which all of Euclid's postulates are true except the parallel postulate. That's not true. Take it back. There are other postulates that aren't true as well. Non-Euclidean hyperbolic geometry, for that, everything is true except the parallel postulate. The geometry on a sphere, or what's called elliptical geometry, I think in general, has more limitations. You have to make some other changes. Anyway, that said, this is new. We're going to make three construction assumptions, which we'll use explicitly. These are obvious, but we're just saying it. Two distinct lines meet at most one point. A circle and a line meet at most 2 points, and two, get rid of that, do this, and two distinct circles meet at most 2 points. All right, and then we're going to make assumptions about transformations. I may list these somewhere in another document. So reflection preserves distance and angle measure. We are going to assume that reflection preserves both distance and angle measure. Okay, that's a kind of a high level assumption, but pretty obvious in terms of our intuition. We are also going to assume that dilation preserves collinearity. That is, if 3 points are on a line and you dilate those, you map those under a dilation, the image points will also be on a line. And that is an example of a relationship that is preserved, not a measurement. Collinearity is a relationship. All right, here are the theorems. First, we have preliminary results. And the first one is that there is a reflection that maps any given point P onto any given point Q. That you could probably prove yourself. That's not too hard. It's very quick, actually. Theorem 2, which is very important, actually, it turns out, in the transformational approach, a little harder to do. A point is equidistant from 2 points if and only if. It goes both ways. If and only if it lies on their perpendicular bisector. So that means if a point lies on the perpendicular bisector, then it's equidistant. If it's equidistant, then it lies on the perpendicular bisector. Seems reasonable, but not so easy to prove. Theorem 3 says that it is sort of an extension of Theorem 1. Theorem 1 said we could map a point to a point with reflections. And Theorem 3 says if you have two segments that have the same length, then one is the image of the other under either one or two reflections. So you can map a segment to a segment of equal length under either one or two reflections. Okay, a corollary is that segments are congruent if and only if they have equal length. So if they are congruent, then it says right here, I'll just say, if they're congruent, then that means you can map one onto the other with a sequence of isometries that preserve distance. So they must have the same length because isometries preserve distance. If they have equal length, then Theorem 3 says they're congruent. We can map one onto the other. So that's the if and only if, and we obviously want this to be true, and now it is a corollary. All right, and then these prove using, so these are no longer postulates, using these assumptions and theorems, we can prove, and only these, we can prove SSS congruence. We can prove SAS congruence. We can prove ASA congruence. We can prove all those things. And each one uses a different one, interestingly, of the construction assumptions, which is why I'm going back. Each one of these use a different one of these. So there's a nice kind of correspondence, nice elegance there in the way that those things correspond. Okay, so that proves the similarity, the congruence. Then we have what's called, and this Henry and I did ourselves. I mean, there is a book written by a professor which is much more complicated and much less intuitive, and this is really ours. We call, well, it was what's called by Professor Wu the fundamental theorem of dilations. And the fundamental theorem of dilations says the following, that if you have three non-collinear points, okay, the image, then the image of a, and where the 3 points are non-collinear and C is the center of dilation. That's where we start. So imagine that. Then it says that the image of a segment under a dilation with scale factor K is parallel to the pre-image, and that it's parallel. That's what it says, that the image is parallel. That's case one. And then case two says if A and B and C are collinear, then A prime, B prime, C prime are also collinear. And in either case, the segment gets stretched by the scale factor. So we know that a segment, one of whose endpoints is the center of dilation, gets stretched by the scale factor and lies on the same line. That we know by the definition of dilation. This extends it to points, to segments for which neither endpoint is the center of dilation. And in that case, there are two segments. There are two cases, excuse me. Case one is if the segment lies on a line from the center, then the image will lie on that same line and will be stretched by a factor K. If the segment is not collinear with the center, then it won't lie on the same line, but it will be parallel. The image will be parallel and will be stretched by a factor K. That's fundamental. That's a really important theorem of dilations, and that's what enables us to prove a bunch of things. Not so easy. So this stuff is the proof. A corollary is that similar triangles have equal angles and proportional sides, because since, as it said, because since parallelism is preserved, basically you can see that angles are going to be preserved. A direction is preserved is a better way to say it. Direction is preserved. And everything gets stretched by a factor K, so all the segments get stretched, so they're going to have proportional sides. So that fundamental theorem is very important, and then with that under our belts, we can prove SSS similarity criterion, which is if the sides are proportional, then the triangles are similar, that is to say the angles are equal. We can prove SAS similarity. If you have two proportional sides and the included angles equal, then the triangles are similar. We can prove AA similarity, which is if you just have two angles equal, then the triangles will be similar. That corresponds to ASA, really, because one side being proportional doesn't mean anything. You need two segments or four quantities to make a proportion. So we can drop the side, and it just depends on the angles. So that corresponds to ASA, basically. Okay, and the rest of it is curricular implications, which we don't have to worry about. So I will post this article, as I said, and you're welcome, of course, to read it. Don't share it, because we're going to publish stuff including this. So I ask you not to share, but you're welcome to read it. Okay, thanks for listening and watching. Let me go back and cancel the